now we can start. Yeah, so welcome everybody. This is our 7th Solar Climate Intervention Symposium, or virtual symposium, and the first for this year, 2024. And it's really exciting to have our 2 speakers today, which is Dr. Sandro Vattioni and Jessica Wan. And we start with Sandro first. We have our usual 20 minutes presentation and then about 10 minutes or a little less for questions. And so the first talk will be chemical and climatic impacts of solid particle for stratospheric solar climate intervention. And Sandro, please share your screen. And then I give you a little note 5 minutes before the end of the 20 minutes. So, okay, this is in slideshow, and then we could, I mean, it's not in slideshow yet.
Yeah, so, yeah.
Yeah, there we go. Okay, go ahead. Thank you.
Okay. Second. So, okay, hello everyone. Thanks for joining, and I'm very happy to be here and give this talk today. Thank you very much that so many of you joined. I will talk about the chemical and climatic impacts of solid particles for stratospheric solar climate interventions. As you might know, sulfuric acid aerosols have several limitations for SAI, and therefore recent studies have shown that alternate materials such as solid particles might overcome some of these the limitations of sulfuric acid aerosols. For example, Dicamide al. 2016 has shown that some solid particles, such as alumina particles and calcite particles, would result in substantially reduced stratospheric heating compared to sulfur-based SAI for a given radiative forcing. Other studies have shown that, for example, alumina particles would result in substantially reduced ozone depletion compared to SO2, SAI via SO2 for a given radiative forcing. Furthermore, Keith et al. 2016 hypothesized that calcite particles could even result in increase of the stratospheric ozone layer by removing HCl from the stratosphere, so by removing chlorine from the stratosphere on the particle surface. However, these studies they are all they have all some limitations. They are, for example, based on simplified modeling or based on assumptions, and this makes them subject to substantial uncertainty. And that's why more research on the potential benefits and risks of solid particles for the use of stratospheric solar climate intervention is needed, especially in comparison to SO2 injections. And that's what I investigated in my PhD during the last 4 years. In today's talk, I want to address the following research question. Compared to sulfur injections, what are the effects of alumina and calcite particles on the stratospheric ozone concentrations, on stratospheric warming, and on the Earth's radiative balance? I'll do that, or I did that, we did that with the following approach. We first performed laboratory experiments on heterogeneous chemistry on calcite particles at the nanoscale. So we first really looked in the lab at the nanoscale, and these results were then implemented into Earth system models, into an Earth system model to look at the impact of this type of solar climate intervention at the global scale. So let's first have a look at the heterogeneous chemistry on calcite particles. So calcite is a base, and it can react with the acids in the stratosphere. So HNO3 and HCl, they are both present in the parts per billion range, whereas H2SO4 is present at much lower concentrations. HCl is the main reservoir species or the major reservoir species for chlorine in the stratosphere, and it's also the end product of chlorofluorocarbons, which are responsible for the ozone hole, which occurs every year. So when we have uptake of HCl on calcite particles, that would form calcium chloride on the particle surface. And with sedimentation of these calcite particles back to the troposphere, this could efficiently remove chlorine from the stratosphere and therefore increase stratospheric ozone concentrations. So we would potentially have a win-win situation by healing the stratospheric ozone layer and cooling the climate in once. However, there is also HNO3, which is a reservoir species for nitrous oxides in the stratosphere. And nitrous oxides also participate in ozone chemistry in the stratosphere. And for example, NO2 deactivates active chlorine. So when we would remove NOx from the stratosphere under present concentrations of ozone-depleting substances, this would result in decreased ozone concentrations due to less deactivation of chlorine. So we need to know how large the uptake coefficients of these acids are under stratospheric conditions. And there are several studies which have already looked at this and measured uptake coefficients of HNO3 and HCl, but very little of them have measured under stratospheric conditions. The uptake coefficients range over more than 10 orders of magnitudes, as you can see here, while uptake coefficients of 10 to the minus 1 would remove the whole reservoir of these two acids from the stratosphere within days. Uptake coefficients of 10 to the minus 5 and lower would likely not do much to stratospheric chemistry. So it's really important to know how effective the uptake of these acids would be on calcite particles under stratospheric conditions. Maybe, potentially, there could also be a sealing effect or a passivation effect with time. So when HCl and HNO3 reacts with calcite and occupies all the reaction sites at the surface, this could result in a continuous passivation of the particle surface, which seals off the interior from further reaction. And with this, the uptake coefficient would decrease over time. So we need to determine the uptake coefficient and to measure the uptake coefficient of these acids under stratospheric conditions. And for this, we need surface-sensitive measurement techniques, which allow to measure the composition of the uppermost surface layers of a calcite sample as a function of time. So we have performed ambient pressure XPS and high ERDA experiments. On the one hand, ambient pressure XPS has a lower depth sensitivity, but it has the big advantage that it allows to analyze the samples in situ under stratospheric conditions during exposure. On the other hand, heavy ion elastic recall detection analysis has a larger depth sensitivity, but you can only analyze the samples ex situ after exposure. So for the rest of the talk, I will focus on the ambient pressure XPS measurements of uptake of HNO3. Because the facility we used, the ambient pressure XPS facility, which is the one at Paul Scherrer Institute at the Swiss Light Source synchrotron at Paul Scherrer Institute. This setup allowed for the first time to measure the uptake of HNO3 under stratospheric conditions on time scale, in situ on time scales of up to 1 day, so 21 hours, as you can see here. This is the resulting calcium nitrate layer thickness or the evolution with time when exposing the sample to 0.6 to 17.6 times stratospheric concentrations of HNO3. And you can see that the resulting layer thickness is between 0.2 and 2 nanometers at the end of the exposure. And this corresponds to an uptake coefficient of about 10 to the minus 4 to 10 to the minus 5. This is rather low. But another interesting feature which we can see, which we can observe, is also that these curves flatten with time. So the uptake decreases with time, which indicates a passivation effect of the surface. So we now put these results into context to other, or we compare these results to other measurements of the uptake coefficients of HNO3 and HCl to other measurements. Our measurements are shown here in green, and the plots on the left and the right-hand side, they show these uptake coefficients as a function of the exposure. The exposure is the concentration of HNO3 and HCl applied at times the duration of each experiment shown here. And there is an evolving picture which one can observe. Particles freshly exposed to the stratosphere, so with a low exposure, have a very large uptake coefficient. And the longer the exposure takes, the more the uptake coefficient decreases. So there is a passivation effect, likely limited through the diffusion of the calcium chloride or the calcium nitrate into the sample. When we now look at typical exposure times of calcite particles in the stratosphere, they have about a residence time of about 1 year in the stratosphere. And when we look at the corresponding exposure, we arrive at uptake coefficients of about 10 to the minus 4 for HNO3 and 10 to the minus 5 for the uptake of HCl. Now we want to have a look what the effect of this uptake coefficient on calcite particles would be on the global scale. So what is the effect on stratospheric ozone? For this, we have implemented a solid particle microphysics scheme in the Earth system model SOCOL. SOCOL is a sectional aerosol chemistry climate model, which also has the option to be coupled with an interactive ocean. So it's a fully coupled Earth system model. And it also incorporates all relevant chemistry to represent stratospheric ozone chemistry. We have used that model to implement solid particles into the solid particles microphysics module into that model. The particles can agglomerate together. They can agglomerate via coagulations. They are subject to sedimentation and advection and wet deposition. And they also interact with the radiative transfer code of the model. And they also allow to represent heterogeneous chemistry on the particle surface. Therefore, this is the first aerosol chemistry climate model, which allows to simulate interactively feedbacks between these individual processes. So we have used this model to look at the ozone response from injecting 5 megatons per year of calcite particles between 30 degrees north and south at 50 hectopascals with a radius of 240 nanometers. And on these calcite particles, we have applied these uptake coefficients for HCl and HNO3. And as you can see, the effect on, or the response on of the total ozone column is relatively small. It's only an increase of about 2% over the south polar region, whereas the same injection scenario for SO2 injections results in ozone decrease of about 7% in the south polar region. However, this is the most likely scenario, but it's subject to some uncertainty. So if diffusion would be very efficient into the sample, the uptake could well be larger than the reported values here. And therefore, we have performed a sensitivity analysis.
Andrew, 5 more minutes.
Yes, with uptake coefficients of 10 to the minus 3 for HCl as an upper estimate. And you can see when we apply an uptake coefficient of 10 to the minus 3, we get an increase of the total ozone column of up to 25%. So an effective healing of the ozone hole. On the other hand, when applying an uptake coefficient of 10 to the minus 3 for HNO3, we would see an ozone depletion of about up to 10% over the poles. But the most likely scenario is rather around the zero line. So it will be likely something in between the extreme scenarios. Let's briefly have a look at the heterogeneous chemistry on alumina particles. Alumina is stable towards reaction with the acids in the stratosphere, so it does the bulk does not undergo any chemical reaction, but it provides surface for heterogeneous chemistry. And for example, chlorine nitrate, one of potential heterogeneous reaction is chlorine nitrate plus HCl, which will activate chlorine into its active form and therefore cause ozone depletion. There was one previous study which has looked at the at this reaction on alumina particles injected from space shuttle exhaust, and we have used that experimental data and extrapolated it to stratospheric partial pressures of HCl, and we derived this uncertainty range for the ozone response. So about 16% in the worst case, but most likely, as for calcite, it's rather a small effect. Here are the combined uncertainty ranges for calcite and alumina injections to the stratospheric ozone column. And we also did a sensitivity analysis for the SO2 injections. By applying realistic uncertainty ranges on heterogeneous reaction rates on sulfuric acid aerosols, and as you can see, the resulting uncertainty range is much smaller compared to the one with for alumina for solid particles. So even though the ozone depletion might be larger for SO2 injections, the uncertainty range is much smaller. When performing the same experiments under 2090 conditions, you can see that the effect or the impact is much smaller due to significantly reduced ozone depleted contributing substances in the future. And when comparing the two reference scenarios to each other, so the reference 2020 to reference 2090, you can see that under this extreme climate change scenario, the effect on the ozone layer is much larger than any of our perturbation runs. Let's now come back to the research questions which I've initially posed. So what are the effects of solid particle injections versus SO2 injections on the Earth radiative balance, stratospheric warming, and stratospheric ozone? So for 1 watt per square meter radiative forcing, we would need much larger injection rates of solid particles because they're much heavier and also have a larger radius, so they sediment much faster, and therefore they have they would also result in a smaller burden in the stratosphere and a smaller residence time compared to sulfuric acid aerosols. However, one of the big advantages of the solid particles is the significantly reduced stratospheric warming. As you can see, especially calcite has significantly reduced stratospheric warming compared to the SO2 injection case. In the upper part of this figure, I now show the resulting ozone column, so the reference scenario, as well as the lower line shows the historical minimum, which occurred in the beginning of the 90s of the last century, which was due to the combined effect of the Mount Pinatubo eruption and the fluorocarbons which we emitted. And as you can see, the uncertainty range for the solid particle cases are much larger, and in worst case up to 2 times larger than the historical minimum, but most likely it will be somewhere around the zero line. So the impacts on stratospheric ozone from solid particle injection is likely better compared to SO2 injections, but it is subject to substantially larger uncertainty. And with this, I want to thank all my collaborators, as well as and especially my supervisors, Gabriel and Tom, for their support. And thank you very much for listening.
Thank you, Sandro. That's great. Very nice summary. So we open up for questions. So if you have questions, please put your raise your hand or put your questions in the chat, either way, and we can follow that. We already have a question by Huai. You want to start? Please unmute yourself and please go ahead.
Okay. Yeah. Thank you, Sandro, for this great talk. I have 2 questions actually about the aerosol microphysical grooves for the sulfate aerosol. So the first one is, how do you consider the aerosol microphysical grooves for the sulfate aerosol? The second one is like, do you think the surface chemical reaction happens on the surface of sulfate aerosol will influence its microphysical grooves? Thank you.
So I'm not entirely sure if I understood the question. So the first question was how aerosol microphysics was implemented in the model.
So it's like, it's totally similar as the sulfate aerosol for the solid particle.
It's so the difference between the sulfuric acid aerosols and the solid aerosols is that if if liquid sulfuric acid aerosols coagulate, they just form a bigger aerosol, but it's still like kind of spherical. But if 2 solids coagulate, they would form an agglomerate. And these agglomerates, they are the agglomerates are significantly, they have a large fraction of like forward scattering, So they are not they are not good backscatterers. So you want to avoid to have a lot of agglomerates, because the agglomerates have a lot of forward scattering, and that's, I think, one big difference in the microphysics of solid particles versus sulfuric acid particles.
Okay.
Or what was does this answer your question, or did you mean something else?
Yeah, that's the first question. I guess the second question is, I'm curious whether, since you do some experimental work to kind of increase our understanding of what happens on the surface of calcite, I'm curious like whether those new knowledge will also like update the aerosol microphysics happens on for the calcite aerosol.
Yeah, I mean, I'm not, I don't think I understand the question. So what?
Yeah, probably a small, yeah, probably can be ignored. Yeah,
Okay,
I guess, yeah, we can talk later.
I mean, yeah, we for sure quantified heterogeneous chemistry on calcite particles, but I don't know what you mean with microphysics. Yeah.
Yeah,
Yeah,
maybe we can talk later. Yeah.
Yeah.
well, maybe we can do some offline discussion on that. That would be good, and we can clarify that. Great. Are there other questions? Don't see anything in the chat or hands. I mean, I do think my question, obviously, the biggest uncertainty seems to be really on the measurement side right now. And what can be done to reduce that uncertainty?
Yeah, so we for sure need more measurements of heterogeneous chemistry on solid particles and on different types of solid particles. I mean, I have now just looked on, or I did measurements on calcite particles, and there are some measurements available for alumina particles, but not under stratospheric conditions in respect to, for example, HCl concentrations. And so what we need is like flow tube measurements to really measure heterogeneous reaction rates on the stratospheric conditions on these particles of not only one heterogeneous reactions as I did, like chlorine nitrate plus HCl, but all the other potential heterogeneous reaction rates as well for different particle types. And yeah, and especially also with different measurement techniques. So we will for sure perform more XPS measurements to do that, but there's also there are also flow tube measurements required. So because like one measurement is no measurement, so we need to have different groups which get engaged in this, and to really reduce the uncertainty. However, you said like so the biggest uncertainty are like the measurements, what is missing is measurements. But one other big uncertainty which I didn't talk about in my presentations is, for example, the whole dispersion of solid particles into the stratosphere. So when you inject SO2, you just need to inject a gas and can forget about it because it will then form sulfuric acid aerosols downstreams. But the solid particles, they might be subject to van der Waals forces, and which makes them cluster together. And so it's still a big question how and if how solid particles could be dispersed into the stratosphere. And that's also another big topic of uncertainty, which needs to be addressed. Yeah.
Plus, then, of course, the impact on the impact side. But there's Tom.
Sure. Downstream.
Can you do one short question, and then we want to...
Thanks, Sandro. A question I never asked you before, although it's kind of obvious. If really by using calcite, the stratospheric warming is a factor of 4 less than with sulfate, would you also expect the changes in the hydrological systems, the precipitation and so on, to also be reduced by a factor of 4?
Yeah, also I don't know whether these these dependencies are linear, but I would definitely also expect reduced impacts on dynamics and like on in the troposphere, and also like in the hydrological cycle in the stratosphere, obviously with less stratospheric warming would be significantly less perturbed. Yeah.
Thanks.
Okay, thanks. Yeah, please stop sharing. And
Okay.
was great. We'll stop the discussion here. Please send Sandro any more questions if you have online. The next speaker is Jessica Wan from Scripps Institution of Oceanography. And she talks about diminished efficacy of regional marine cloud brightening in a warmer world. So Jessica, thank you for sharing. And please go ahead. As earlier, I let you know when we are like almost 5 minutes to the end of the talk. Thank you.
Perfect. Thank you for the introduction and for inviting me to speak. I'm excited to help kick off the first symposium of the year. My name is Jessica. I am a fourth-year PhD student at Scripps Institution of Oceanography at the University of California, San Diego. Today I'm going to be presenting on some work that is currently in review, entitled The Diminished Efficacy of Regional Marine Cloud Brightening in a Warmer World. And this is work in collaboration with Jack Chen, Simona Tilms, Matt Luongo, Yaga Richter, and my advisor, Kate Rickey. All right. So we just heard a lot about potentially a more globally focused geoengineering idea. Today, I'm going to be convincing you that interest on regionally focused interventions are also on the rise. And probably the most iconic event that kind of inspired me to get started in this work was this work in Australia, where scientists were trying to brighten the clouds right over the Great Barrier Reef in an attempt to cool just temperatures over the reef to combat some of the effects of climate change. There's also been some work in China looking at weather modification over India, weather modification over China, the size of India, to try and modify precipitation and potentially boost agricultural productivity. There's been a number of studies on potentially doing solar radiation modification for extreme heat management, and additionally work not in the solar space, but on the artificial upwelling end to try and reverse droughts in the Sahel. And probably most closely linked to the work I'm going to be talking about is this recent paper by Haruki et al. On using marine cloud brightening in an attempt to change various climate tipping elements in the climate system. And so marine cloud brightening in particular is a proposal that presents a good opportunity potentially for regional solar geoengineering. And just to reorient ourselves from the last talk, we're now moving way down into the atmosphere to the lower layer, brightening these lower marine stratocumulus clouds. And just so everyone's on the same page, the goal of marine cloud brightening is to cool the Earth by seeding the lower atmosphere with potentially sea salt particles in order to form these brighter marine clouds. And kind of the observational analog for this is ship tracks. Ship tracks are produced by ship exhaust seeding these lower clouds, and we can observe these in satellite records. The reason marine cloud brightening is particularly good for regional solar geoengineering is that it is able to be deployed over a generally smaller area than some of these other technologies, and can potentially be leveraged to achieve some sort of regional, physical, or sociopolitical objective. So, for example, this Great Barrier Reef initiative. And so the question that we're asking for this project is whether or not regionally focused marine cloud brightening in the North Pacific can be used to mitigate extreme heat in the Western United States. And this question is interesting for 2 reasons. The first is that the Western US is already experiencing record-breaking heat waves due to global warming. I'm originally from the Pacific Northwest, and there was a big heat wave, I think almost 3 years ago now, that killed hundreds of people. It was really quite an extreme event, both bad for the US and Canada. Not only was this bad for the region, it was one of the most extreme events globally ever, very, very out of sample for this region. And it had effects on the local economy as well, on the fishing industry. So these heat waves are already happening, and they have real impacts for people. The second reason this question is interesting is that the subtropical northeastern Pacific has already been identified by a lot of the kind of solar climate intervention literature and the aerosol cloud interaction literature as a susceptible region to cloud brightening. And so the region we're talking about here is this patch of low marine stratocumulus clouds off the coast of California. This is a plot from the ISCIP satellites series of low cloud fraction. It's the North Pacific. This region has been identified as one of these 3 main stratocumulus cloud decks that are in a lot of the early marine cloud brightening climate modeling studies. The North Pacific, South Pacific, and South Atlantic are kind of those 3 classical regions. And like I mentioned, it's been a topic of interest in the aerosol cloud interaction community as a region that might be susceptible to aerosol perturbations. And so this subtropical northeastern Pacific region is kind of the classical region. We're also testing an alternative hypothesis here that seeding clouds in the mid-latitude North Pacific, kind of near the Aleutian Islands, might be able to elicit a remote response to cool our target region over the Western US. And so kind of the motivation behind this theory is looking at the climate dynamics literature, a nice paper by Yue Dong, 2022, where the authors cooled this region here in the South Pacific and found that they were able to kick off a series of dynamical feedbacks across the entire Pacific basin just by cooling this little extratropical region in the Southern Pacific. And the idea here is you cool these local sea surface temperatures, the mean wind pattern in this region will advect the cooler temperatures equatorward. You're going to get a strengthening of the subtropical high, which is shown down here. You speed up the trade winds, you kick off a bunch of feedbacks like the wind evaporation SST feedback, and this will enhance, spread, and sustain your cooling throughout the basin. And so the question we're asking here is, well, when we look at the modeled low cloud cover in the model we're using for the study, we see a huge patch of low cloud cover in this mid-latitude region. Could we potentially elicit a similar response, but in the North Pacific now, to get this cooling to spread across the basin and hit our target region in the Western US? And so to do this, we're using the Community Earth System Model version 2. The approach first starts by assessing where in the large ensemble of this model do we get the highest amount of low cloud cover and thus the highest brightening susceptibility for a marine cloud brightening study. And so we look at all of the grid cells in this North Pacific region, we rank them from highest liquid water path amount to lowest, and we pick the ones up to a 2% global ocean area threshold to then make what we're calling a seeding mask. And so for these highest ranked susceptibility grid cells, we, in the model, increase the cloud droplet number concentration to 500 particles per centimeter cubed in the lower boundary layer to that 2% global ocean area. And we turn on marine cloud brightening for 9 months out of the year. So we leave it off for winter when probably there would be less incoming solar insolation. And so we develop these masks for both the mid-latitude and subtropical region as sort of our MCB intervention. And you might be wondering, well, why did you choose this approach? And we argue that this is sort of a good way to look at the question. If you assume that you have a limited amount of resources and you're deciding where you can go out in the world and have the greatest brightening and cooling effect. So this is sort of an equivalent effort level approach. There are obviously other factors that would be considered in a real world decision, including negative spillover to other countries and cost effectiveness. This is kind of just one simple approach to get us started. Okay, so once we develop those masks, the last step is to put it in the model. We're running a fully coupled cyclical simulation with and without marine cloud brightening. And so what I mean by cyclical here is that we have annually repeating decadal mean emissions for both a present day condition, so average between 2006 and 2014, and a future run average between 2045 and 2054 under SSP 245. And so what we do here is we run these same decadal conditions every year for 85 years. We take the last 30 years for analysis for each of our control subtropical and mid-latitude MCB simulations. Okay, so that's kind of the whole setup here. Let's get into some results. The first big takeaway of this work is that under 2010 present day conditions, both of our marine cloud brightening strategies in the subtropics and mid-latitudes are able to produce strong global mean cooling. And so here what you're seeing is those same cloud cover maps as before from observations and from the climate model we're using, and the temperature response from marine cloud brightening for the mid-latitude intervention and the subtropical intervention in panel D. And this is both under 2010 conditions. And what we can see here is that we're getting pretty ubiquitous cooling for both of these interventions under present day conditions. You might argue that there's maybe a little bit more cooling in this mid-latitude intervention, but if you're looking at this low cloud cover in map B, you might be wondering, what is the effect of this really, really high low cloud bias in the mid-latitudes compared to the satellite record? Is that causing this larger cooling effect in the mid-latitudes? And to kind of dive into that, we calculated a normalized cooling by the global mean forcing response due to these interventions. And we find that when we normalize by the total forcing of each of these simulations, the global cooling is in fact smaller for the mid-latitude MCB intervention than the subtropical one. You can see that by these numbers in the top right corner. But actually, when we look at our target region and the black polygon, we actually still get larger cooling in our target region from the mid-latitude marine cloud brightening rather than the subtropical one. And so potentially the mid-latitude intervention is still more effective at cooling over our target region under current conditions. And we link this, we hypothesize the mechanism is probably similar to the one proposed by the study by Yue Dong, whereby you get this mean wind advection of the cool temperatures. You get a pileup of high sea level pressure anomaly that speeds up the trade winds and kicks off all of these Rossby and equatorial processes to kind of sustain that cooling throughout the basin. This mechanism is likely still happening in the subtropical case, but the initial cooling is potentially a little bit smaller, and so you don't get as large of a feedback. Okay, so we find that both of these interventions can cool globally. We also find that both of them can reduce dangerous summer heat risk under present day conditions. And so what you're seeing here is the change in relative risk for various heat thresholds defined by the US National Weather Service. These are derived from apparent temperature calculations, and apparent temperature is essentially a more human relevant metric of temperature that takes into account things like relative humidity. You can see here that the mid-latitude changes are represented by the orange circles, and the subtropical ones are these blue triangles. And we get the largest reductions in the highest heat threshold, the dangerous heat threshold, and the mid-latitude marine cloud brightening reduces the risk substantially more than the subtropical one for our target region. The effects are a little bit smaller or non-existent for the lower heat thresholds. And what you see in these maps are then the spatial distribution of these changes in relative risk in units of people days per summer for that danger threshold. And you can kind of see that, you know, we're getting a pretty strong reduction in relative risk of dangerous heat exposure for most places. The story changes, though, when we look at what happens under our future run, our 2050 run, and we find that not only are our interventions ineffective in 2050 at reducing dangerous heat, they're actually sometimes counterproductive. They cause increased exposure to dangerous heat for the same places for the same intervention. And that's potentially a concerning result, considering we're not ready to deploy marine cloud brightening today. And this is something that we might consider doing in the future. And just this change in the base state can alter the impacts of these interventions. Okay, so this is the result for our target region. We find that also there are unintended side effects in remote regions under our 2050 run. And so these are showing you the responses to the mid-latitude marine cloud brightening for apparent temperature and precipitation for our 2 time periods. And you can see that probably the most striking one is this warm patch we're getting over Europe in the 2050 mid-latitude marine cloud brightening run, which suggests that we're actually causing hotter summers than would otherwise occur without any marine cloud brightening under 2050 conditions. There's also some precipitation responses in both time periods that would be potentially negative as well. But let's dive into this European heating. Why does that happen? We propose that this might be linked to a state-dependent AMOC response due to both a warmer greenhouse gas warming effect and our marine cloud brightening response. And so basically, AMOC is much weaker in CSM2 under 2050 conditions compared to present day. And when we apply our marine cloud brightening perturbation in this mid-latitude region, we're spinning up AMOC substantially in its weakened state. And you can see that here by this strong orange colors.
You have 5 more minutes.
Thank you. When we zoom out and look at the response to all the different simulations, we see that, well, let's orient. These top ones are the 2010 ones, and these bottom ones are AMOC strengths for 2050. We can see that we are getting this dramatic weakening across all of our simulations for the 2050 ones. And marine cloud brightening is able to spin up AMOC from our control more under 2050 conditions than the 2010 ones. And that suggests that potentially AMOC is easier to perturb when it's weaker under 2050 conditions, and that when we cool at one latitude, we have to warm at the same latitude, but in a different location in order to balance that energy. And that has to happen then in the Atlantic, since we're cooling in the Pacific. So we're warming the Atlantic, warming over Europe. Okay. So I'm just going to summarize now kind of the key takeaways. So the first was that under present day conditions, both of our marine cloud brightening strategies were able to cool our target region over the Western United States, and they were able to reduce the dangerous summer heat exposure over the target region as well. But when we fast forward to mid-century warming conditions, both of the strategies become ineffective and actually produce hotter summers in our target region and other parts of the world than would otherwise occur without marine cloud brightening. We attribute this warming effect potentially due to the state-dependent response to the Atlantic meridional overturning circulation, both due to these warmer conditions and our regional marine cloud brightening intervention. And finally, that probably the biggest high-level takeaway here is that regional interventions that appear promising today may not remain effective in a warmer world. Finally, I just want to thank the various funders of this work, particularly the NSF NCAR Early Career Innovator Program. They connect me with a lot of great collaborators on this project. And with that, I will take questions, maybe a little early.
Thank you. No, this is great. Thanks for the great talk and also for ending early. So that means we do have enough time for questions. And I see, Rob, you have a question in the chat. If you want to just unmute yourself and raise the question, that may be easiest. I don't.
Yeah, sure, I can do that. Yeah, yeah. Thanks, Jessica. Really interesting talk. Do we know? Just one specific question. Do we know how AMOC is handled in CSM, say compared with other models? Is it stronger? Should we expect something similar across model behavior? That's what would be kind of interesting to know your thoughts on that. Thanks.
Yeah, that's a great question. I think when we look at like a lot of the CMIP6 projections, CSM2 falls pretty much in the middle with all the other models on its projected AMOC response. And so I think we could expect a similar response with other models. It's pretty on par with other models participating in CMIP6.
Yeah, thank you.
Other questions? Hai Long, please go ahead. Thank you.
Yeah, thank you. Very interesting work. So I have one model setup question and another question about the interpretation. So the setup question is that we run the model with 2010 emissions versus 2050. Do you have also aerosol changes? Because in your perturbed marine cloud brightening domains, you fixed the CDNC perturbation, right? So how about the other regions respond to the aerosol change?
Yeah, so the background emissions are set to that decadal mean as well. So it's kind of like we're setting the world back into this mean state. All of the background conditions would be changed between the present day and the future run, if that makes sense.
Did you compare the 2050 and 2010 other unperturbed regions, how the cloud responds to the aerosol difference in aerosol?
Do we compare the unperturbed? So just compare the controls, you mean, between the two time periods?
So when you perturb the cloud drop number to 500, that's only for the domain, small regions, right?
Mm-hmm.
So the remaining parts of the globe, did you compare how different the clouds are?
Let's see. Yeah, I didn't show these ones. This is kind of the global picture. I guess I'm not sure I fully understand the question, but yeah, the 500 is fixed for both time periods, and so it would be operating under different background aerosol conditions between the 2010 and 2050 run. And so if there's potentially fewer aerosols in the 2050 run background state, then potentially the 500 will have a larger effect in 2050.
Okay.
Yeah.
All right. Thank you. I do have another question, if I could ask. When you compare the efficacy between the mid-latitude and the subtropics, the difference seems like not very big, but I wonder if they're actually comparable because the base state are different. The temperature, like subtropical is warmer. Like when we study the high latitude change, like Arctic amplification, right? So when you apply a forcing, same forcing, the temperature response might be different. I wonder, have you thought about the, and also the forcing, the short wave, downward short wave radiation is also much stronger in the subtropics. I wonder, have you thought about how to have a fair comparison between those two numbers?
Yeah, that's a good question. So I think by design, we chose not to prescribe or fix like radiative forcing as our intervention because we wanted it to be more kind of physically realistic, where if you had, like, say, as a policymaker, you had a set amount of resources and you were going out to do this, what could you achieve forcing wise and temperature change wise for that set resource? So that was a design choice. There have been other studies that have tried to hit a certain global watt per meter squared change. And potentially those are more comparable in a different way. But we chose this design as kind of more of a regionally realistic way that this intervention might go about. But yeah, that's a great question.
Thank you.
Thanks for the answers. Are there any other questions? Jessica? Yang, please go ahead and raise your question. I just see you posted something.
Oh, yes, I have my question there. maybe following up Helen's question, I still didn't follow the detail. Did you use different areas even under future conditions because of climate cloud feedback, the cloud pattern may shift?
No, so the areas are exactly the same for the two time periods. But that is correct that potentially, you know, the most optimal regions would change under 2050 conditions. We're using the lens historical data to kind of fix those regions and just change the background conditions. But absolutely the cloud coverage could change under 2050, and potentially that area would need to shrink or get larger and shift.
Yeah, because in principle, you would do it in a more adaptive fashion and optimize your application according to future conditions. And your present day results looks quite promising. I didn't even see any place getting warmer. Usually, when you perturb a local region with a cooling forcing, you will end up with some remote heating, remote warming out of the application region. But for
Right.
your present day results, that seems to be all blue.
Yeah, I guess you could see there's a little bit in the Atlantic and maybe over the ocean, but yeah, it was pretty surprising. A good surprise, I guess.
Okay, yeah, thanks. Haruki, you want to unmute yourself?
Yeah, hopefully a quick question, but so your simulations are time slice, correct?
Yes, they're kind of repeating the same 10-year background conditions, but with a fully coupled simulation. So like, I mean, cloud brightening is applied every year as well.
Great.
But just repeating that same year over and over and over to get statistical significance. It's kind of like a alternative to running multiple ensemble members.
Yeah, I'm just curious how long so I guess in your 2050 runs, how long it takes for this, I guess, do you see an initial cooling and then eventually the AMOC spins up and warms up the northern hemisphere, or do you never see that cooling at all? Or like what kind of time scales do you end up seeing?
That's a good question. I think there is a transient response, definitely in the 2010 case. I believe I have some as well for the 2051 in the first like 4 years of the spin up. But honestly, we're taking a perturbed state 2050 and just immediately turning on a lot of marine cloud brightening. So we're taking that whole 50 years as really just spin up, and I don't know how much I trust from it with like model drift and all that.
Okay, thank you.
Yeah.
Okay, well, great. If there are no more questions, we are right at 10 a.m. my time at least. And so thank you so much, everybody who participated and who presented, definitely Sandro and Jessica. I'm looking very much forward to the Gordon Research Conference happening, and many of you hopefully will be there. And else we're aiming for our next symposium in a month. We'll give you updates on the speakers later. Thank you very much, and have a good weekend.